So welcome back, everybody, to another day of calculus. I'll try to share with you this PowerPoint stuff today, and I'll try to do a full screen slideshow. So I think that I'm probably not going to be able to see the chat when I'm doing this. So you may have to yell out. But are there any issues seeing the screen? Can you all see the screen? Okay. So this lesson, it's about, the section is called derivative as a function, but there's so much more information in this section than just considering the derivative as a function. And I will do this lesson assuming that you've watched my videos, which introduce some of these concepts. Definitely stop me if you have any questions or comments as we go through. So yeah, in the previous lecture, in the previous section, we defined what is the derivative. It's the limit of the difference quotient that you see there. And in fact, I gave you another definition too, where you could also think of it as the limit as x goes to a. And sure, we computed the derivative for specific values of a. But it's also interesting and useful to consider the derivative function. And what I mean by that is, well, at any point, you can calculate the derivative for a differentiable function. So you take as an input a point, and as an output the derivative at that point. And so this defines for you a new function, which we notate f prime of x. So you're really just substituting variable x for constant a in the definition of the derivative. And there you can see f prime of x is limit h goes to 0, f of x plus h minus f of x over h. And alternatively, if you are thinking of graphing a function, you write y equals f of x, you might write y prime or even y prime of x. And you can just see that definition there, say f is differentiable on a domain, on an interval, if the derivative exists at all points in that interval. So this first example, we actually did something quite similar to this sort of by accident last time. I think I did x squared minus 10x, but instead of computing it at a point, I just went through the derivation with x as a fixed variable. So you've seen me do one of these compute f prime of x's before, but I will go through like the book's argument here again. So compute f prime of x for f of x equals x cubed minus 12x, and find an equation for the tangent line. And you get these nice pictures here. So x cubed minus 12x, that's what we call a cubic function. Cubic functions typically will have these two, this one local minimum, the one local maximum. You know, see those like two bends, and then they'll travel off to negative infinity and positive infinity. So all graphs of cubic functions typically have that character. And you see a visualization of the tangent line there. So like what would you do, like before showing you the proof, what do you have to do to compute this? So you need to go back and write down the definition. So you'll go back and write down, literally you'll write down limit as h goes to 0 of this, and you'll substitute in x plus h and x into that definition. You'll do some algebra to hopefully cancel out the denominator, and you'll find a formula for f prime of x. In this case, the formula will turn out to be something like 3x squared minus 12. But let's see how that works out. So here they're doing it, I guess, a little bit differently than I would do it on the board. Like for my board work, I would just, for my step 1, I'd just say f prime of x equals this limit, like they're doing in step 3. But what they're doing, it's not bad. They're trying to do some work on the difference quotient first. This is the numerator of the difference quotient, so they're trying to do some algebra there, compute and factor out the h, and we'll go through that. So yeah, I guess maybe the hardest thing about this problem is actually computing x plus h cubed. If you're not familiar with that, I mean, this is basically the formula here on the second line. There's something called the binomial formula. You can look up the binomial formula to compute things like a plus b to the n. And maybe I won't say like too much else about that, but yeah, for computing x plus h cubed, it's you get the 1 cubed term, you get x cubed, and certainly you also get h cubed, and there it is. And there's these 2 terms in the middle, these 2 quadratic terms, and well, one's quadratic in x, one's quadratic in h, but yeah, so like maybe I'll stop myself. I won't do a full explanation of the binomial formula, but we can, that's a key word for you to look up, and we can certainly talk more about that in office hours. It's really the key to doing this. Then you subtract out the x cubed minus 12x. So you're going to get a cancellation with an x cubed, and you're going to get a cancellation with a 12x. And that's leaving you terms that only involve h that allow you to then factor out h from everything. When you divide by h and simplify, you get that nice cancellation, and then you're just left with 3x squared plus 3xh plus h squared minus 12. And finally, you can compute the limit. So like what I might do at step 1, they're now doing this first and just doing the algebra as a preliminary step. So you compute that limit. You can see what you've got is, what happens in 3x squared plus 3xh. H goes to 0, that's going to vanish. H goes to 0, that h squared is going to vanish. And you're left with 3x squared minus 12. So like as we predicted at the beginning, later on we'll learn formulas so that you'll be able to do these derivatives of polynomials in your head, and you won't have to go back into the definition every time. So x is your input and your output is 3x squared minus 12. That's telling you that at the point x, the slope of the tangent line is 3x squared minus 12. So you've got now a general formula for the slope of the tangent line at any point. So you can simply plug in -3 into the derivative function. You can see that we do that there in the last displayed equation, and the answer is 15. So how do you, so you use point slope formula, your slope is 15, the x value is -3, and the y value you get by plugging -3 into f of x, not f prime of x, but f of x. So f of -3 is 9. Plugging that into your original equation. So you get a slope 15 and a point -3, 9. So you use that point slope formula. You can see us plugging it in there. You get that formula for the tangent lines. So that's where this kind of purple line came from. So any questions or comments about that derivation? And so just more more examples there. Try to maybe hide this, hide the meeting controls. Hopefully I can get back to them. So there's another example here to prove that y equals 1 over x squared, that's x to the minus 2, is differentiable and calculate y prime. And you're really going to go back to the definition here. And once again, the hardest part about this is algebra. So when you just go back to the definition, and it's kind of funny, like in the previous one, they went back and did some algebra first, but here they're switching to the style that I prefer to do all these problems, which is just write down the definition immediately, and then substitute in for f of x. And you see you've got this improper fraction. And whenever you've got an improper fraction, what you should do is find a common denominator and just rewrite it as a single fraction. And that's what the next two inequalities are doing. The common denominator here you get by multiplying both of them together. So it's x squared times x plus h squared. So in the numerator, you're going to get x squared. And then in the numerator of the other one, you're going to get x plus h squared. So that's where we're getting x squared minus x plus h. Everything divided by the common denominator. And then that's being divided by h, which is the same thing as multiplication by 1 over h. So you can see like this is like your first step really, that you've converted it to 1 over h times all this business. And the only way you could possibly continue to solve this problem is by seeing if you can, get a factor of h in the numerator that you could cancel out. Like otherwise, basically, you can't do this. And so for that, you should expand out. You should expand out this x plus h squared. And I think they're skipping that step, but that's what they're doing. So when you expand that out, you get x squared plus 2xh plus h squared. And the x squareds will cancel because you're subtracting. You'll be left with 2x with minus 2xh minus h squared. And then you can see factoring out the negative h from that. That's the next thing that they write down. Just skipping a little step there. Now you cancel out those h's, and now you can take the limit. So now you can do the limit by just substituting h equals 0. And you end up with minus 2x cubed. Of course, is going to be valid whenever x is not equal to 0. There's a rule that you can use to calculate this called the power rule. We'll talk about that in a moment. But like if you've got y equals x to the minus 2, there's a way to do this without going through the computation. So you can just immediately say this is going to be minus 2x to the minus 3. And what you want to think about doing is taking that exponent and just bringing it down out front, and then subtracting 1 from the exponent that's there currently. Do you see that? So if you bring down the exponent and subtract 1 from the exponent, you get minus 2 times x. And then minus 2 minus 1 is negative 3. So you get minus 2x to the minus 3. This rule works for every function of the form x to the n. It works even if n is not an integer. Like if you had y equals x to the 1/2, the derivative of that is going to be 1/2 times x to the minus 1/2. And so you can get all those derivatives without having to actually calculate it. We'll talk about that in a second. Just a little note about the notation. The prime notation, that's because this apostrophe or this symbol is called a prime. So you read that as y prime or f prime of x. So introduced by the French mathematician and physicist Lagrange. But there's another notation for the derivative that was introduced to Leibniz. He was one of the original inventors of calculus, along with Newton. And you would write df dx for this. And like, let me explain for just a second why df dx makes sense. Because the derivative is a limit of different quotients. You go like all the way back to the beginning. This limit of a quotient of differences. I mean h, but h is really x plus h minus x, right? So Leibniz wanted to emphasize the fact that it was a limit of a quotient. And so he used df dx to remind you of that. So d for a derivative and dx to remind you that x is the variable. So this is to remind you that it's a limit of fractions, even though this itself is not a fraction. It's just notation equivalent to writing f prime of x. So like what this literally means is limit as h goes to 0 of the difference quotient. And of course, if you're writing y equals f of x, then you could write dy dx. And so yeah, in the previous example, dy dx is minus 2x to the minus 3, or you might say df dx is minus 2x to the minus 3. But when you just substitute in the function instead of the letter f, it's common to write d over dx, thinking of this as like an action that you're performing on x to the minus 2. So the action of taking the derivative results in minus 2x to the minus 3. The awkward thing about this is that there's no clear way to like give an input. So to specify the value of a derivative for fixed value of x, you would draw this vertical line and say x equals 4. So that's kind of like a drawback of this notation, but it's useful in certain contexts. So what's the constant rule? I mean, we're going to see a bunch of quote unquote rules, but it's just stuff that we've derived. We've derived this before. For any constant, the derivative is equal to 0. And that's what this is saying. They're just writing it in that Leibniz notation. You can see this proof there, but like we did this proof, in class last time. Here they'll call this the X rule. I don't know, it doesn't really need a name, but we did this last time too. We saw that for any linear function, the derivative is equal to the slope of that line. Here your linear function is just f of x equals x. Its slope is equal to 1, so its derivative is equal to 1. And of course you can calculate that out as you're seeing there, but more generally, if f of x is ax plus b, then the derivative is equal to a. And these rules, you might want to note them. They're in your book, of course, too. But you might want to note them and commit them to memory. I would say commit them to memory and also be able to show them. There are some later on that it's maybe too hard to show them, and you would just memorize them. But for these, like you memorize them and if somebody asks you, you'll know how to prove it. Yeah, so here's the power rule. So this is one that we're not going to prove, we just commit to memory, which says the derivative of x to the n is equal to n times x to the n minus 1. And so we've already seen this because we saw this with x to the minus 2. The answer was minus 2, x to the minus 3. We saw it here with x to the 1, right? F of x equals x, but x is equal to x to the 1. So its derivative, therefore, should be 1 times x to the 0. And anything raised to exponent 0, like a variable raised to exponent 0, that's equal to the number 1. 0 to the 0 is a different story. That's an indeterminate form. But for any other number raised to the 0 power, that's equal to 1, sort of just by convention or definition. So this rule definitely fits into the power rule. But the power rule works for any n, like whether or not it's an integer. As you can see, like it works for these fractions. Even works for the square root of 2. X to the square root of 2, its derivative is root 2 times x to the root 2 minus 1. For more information on what even is x to the root 2, I'd be happy to talk to you about that in office hours, about how to like define that function. These exponent functions are easier for us to understand when it's like x squared or x cubed, or even x to the minus 3/5. You can handle that because that's like 1 over x to the 3/5, and x to the 3/5 is like the 5th root of x to the 3rd. So at least that you can interpret, but x raised to an irrational power is a little harder to interpret. But perhaps we can talk about that in office hours. And of course, you can do this with any variable. Not just see some examples there. And I'll give you some homework where you'll have to do some examples too. But it's just practicing the mechanics of using this formula. It's not a huge deal. Linearity rules, these are basically the same thing as limit laws. That's how you should think about it. So any limit law that you have is also going to have a corresponding derivative rule. And the reason why we do linearity rules is because it allows us to break up a derivative into a smaller problem. So like if f was x cubed and g was 12 times x, then you could simply calculate the derivative of x cubed, which is 3x squared, separately calculate the derivative of like 12x, which is 12. Add them together, and that's going to be the derivative of x cubed plus 12x. So that's how I was able to do this derivative problem at the top of the class so quickly, because I was just applying these like sum and difference rules. And for any constant, yeah, you can pull out the constant, like derivative of 3 times x squared. What's that going to be? It's going to be 3 times the derivative of x squared. So it'll be like 3 times 2. Derivative of 3x squared you can calculate to be equal to 6. I'll say a little bit more about this with an example. Let's do like a Desmos example. Check the chat also and respond to messages. Let's stop sharing just a minute and let's do some Desmos work. Like, let me show you how to use this linearity derivative rule in action. We had this what was it, x cubed minus 12x? It was something like that. If it wasn't exactly that, then it was something like that. And here you see it graphed on Desmos. You also saw a picture in the book. And this Desmos graph looks a little bit more squished because the scale. on the x and y axis are a little bit different. So this is my, I'll call this h of x. And h prime of x, well, it doesn't want to give us the formula, but it'll show us the graph in blue there. H prime of x, we calculated, it was 3x squared minus 12. And Desmos doesn't really like me to do this because, like, if I define h, it wants to calculate for me what is h prime. It's kind of upset that I'm telling it that h prime is something. But I'm telling the truth. So this is h prime, and we calculated this from the definition earlier on in the class. But suppose that we wanted to use the power rule and the constant rule and like the x rule, like suppose we wanted to use all those rules. So how could we do it? So what you would do is you would say like x is 3x squared, like f of x. We say like g of x is minus 12x. And maybe I don't need to graph those. What you're going to do is you're going to say like, if I want to calculate, like I know that h of x equals f of x plus g of x. So what you're going to say is if I want to calculate h prime, then I can do that by calculating f prime separately and calculating g prime separately, and then adding them together. So if I want to calculate f prime, I just use, well, the constant rule says I can type 3 and then multiply that by the derivative of x squared. The power rule says that the derivative of x squared is 2 times x. So that's 6x. And then, sorry, I typed in the wrong thing for f and g, didn't I? Because I wanted to write h is equal to f plus g. So h is x cubed. H is x cubed minus 12x. So f would be x cubed and g would be 12x. You add them together to get h, and we know that h prime is 3x squared minus 12 because we calculated it, but I could also get it by first calculating the derivative of f of x, using the power rule and getting 3x squared, then calculating the derivative of g of x using maybe the constant multiple rule to pull out the constant negative 12. So this is going to be negative 12 times the derivative of x, but the derivative of x is equal to 1. And so this is going to be also the derivative of h of x. So the point I'm emphasizing is that yeah, you could calculate h of x immediately from the definition, or you could use these derivative rules to break it up into two pieces and then calculate the derivative using the rule of each piece. And either way you do that is valid. You should use the derivative rules so that you could eventually calculate this in your head. And then if I just ask you on a test to use the limit definition of the derivative, that's when you would calculate the derivative, using that limit. Okay. So any questions or comments on that? Okay, well, I'll continue on with the PowerPoint. So these are the rules, true, but it's not that the rules that are important, it's how you use them. And their proofs come from the limit laws. So you write out the left-hand side, f plus g prime. So the limit as h goes to 0 of, of f of x plus h plus g of x plus h over h. You separate that out into two limits, and you see that's equal to f prime plus g prime. Yeah, cool. So, I mean, actually, I guess me and the textbook author are like mind because they're going to do the same thing, but they're going to use f of t equals t cubed minus 12t plus 4. So calculate the derivative, find the points where the tangent line is horizontal. So yes, you could plug into the definition, but the easier way to do it is to use these derivative rules. To break this up as 3 derivatives, you can see that in the second line using some and different rules. And then you pull out this number 12. And derivative of a constant is, of course, 0. And now you've got derivative of t cubed by the power rule is 3t squared. Derivative of t is equal to 1. The answer is 3t squared. Basically the same thing I just did, except they use variable t. And then they add plus 4. And remember, their picture looks a little bit different because they have a different scale on the horizontal axis. So next, find the horizontal tangents. That is to say, find the tangent lines that have a slope equal to 0. And you've got a formula for the derivative, so just set it equal to 0. How do you solve that? Well, just factor out 3 and t squared equals 4. So the answer is t plus or minus 2. And you found the x values, but you need to find the points on the graph where the tangent line is horizontal. So you need the y values as well. So just plug in 2 and negative 2. You can see those points are listed there on the graph. See, it totally makes sense. Those are the 2 points where the tangent line is horizontal. Pretty cool stuff. It's just another example. So this is going to be calculate that derivative by breaking it up into 3 pieces and then applying the power rule to each piece. So and we call that term by term differentiation. So they're no longer going to be justifying the intermediate steps. You do have to know that square root of t is the same thing as t to the 1/2. So bringing back some algebra there. And yeah, you look through that. So the derivative, you say the derivative of t to the minus 3 is minus 3t to the minus 4 using the power rule. The derivative of t to the 1/2 using the power rule, you bring down that 1/2. And then 1/2 minus 1 is minus 1/2. So you get 2 times 1/2 times t to the minus 1/2. Finally, you're subtracting the derivative of t to the minus 4/5. So the coefficient becomes minus 4/5. So t to the n is n times t to the n minus 1. So you get minus 4/5 and negative 4/5 minus 1. That's negative 4/5 minus 5/5. So that's t to the negative 9/5. You just clean up the algebra, cancel out those 2's. 2 negative signs make a positive. You get 3t to the minus 4th to the minus 4 plus t to the minus 1/2 plus 4/5 t to the minus 9/2. And the calculation asked us not just for the general formula, but for the formula at t equals 1. So to find the formula at t equals 1, you simply plug in t equals 1. And 1 to the minus 4th, that's 1 over 1 to the 4th, that's equal to 1. 1 to the minus 1/2 equal to 1. We're getting negative 3. 1 to the minus 9/5. Like you see the pattern, 1 raised to any exponent, it's just going to be 1. So minus 3 plus 1 plus 4. Add those up as usual, finding a common denominator. The result is going to be negative 6/5. Yeah, what can you get from the derivative function? This is just reminding you the derivative is the slope of the tangent line at that point. Actually, I'll talk more about this later, so I'm not super concerned about that right now. Yeah, I'm not super concerned about any of this. I mean, this one we can at least. Okay, so yeah. I mean, I'll talk through how to do this problem. Basically, what we're going to learn is that whenever you have a function that's increasing, like trending upwards like this, increasing, that corresponds to the derivative being positive. Whenever you have a function that's decreasing, that's going to correspond to the derivative being negative. And we've already seen, like when you've got derivative equal to 0, that's horizontal tangent. So whenever you've got this horizontal tangent line, the derivative is equal to 0. So it could perhaps be switching from positive to negative. So you've got a situation here where you've got a function increasing, has a local maximum, and then starts decreasing. So the derivative is going to be positive 0 at 4 and then negative. So this choice B cannot be the derivative of the blue function because it's not 0 at the point 4. So here at the point 4, we definitely have a horizontal tangent. So this cannot be the answer. You need something that goes positive, it's 0 at 4, and then goes negative. That's exactly what happens here. So choice C could be the derivative. So that much I'd like you to know, but you don't have to know anything else from the previous few slides. It's really just, looking for these local max and local min. Those are the places where the horizontal, where the tangent line is horizontal, where the derivative has to be 0. And you can use that information, plus increasing function, derivative is positive. Decreasing function, derivative is negative. And you see the horizontal tangents exactly line up where this function has zeros, crosses the x-axis. So that's what I'd like you to do. Yeah, the number E, what can I say about this? What the textbook has done so far, and this is why I don't like using textbook slides because I don't always agree with the presentation. Um, yes, the number E is an irrational number. Yes, the first three significant figures, 718, so 2.718. Uh, yes, it's true that the number E is the unique number such that the derivative of e to the x is equal to e to the x. All that's true. It's kind of a backwards way to introduce the number e, however. So I'll give you a better explanation of what is the number e later on. The number e was discovered in the 1700s by finance people that were trying to figure out a compound interest formula, actually. So I mean, there's an interesting story behind that. So like I'll bring that all together later on. But for now, yes, this is an exponential function. I'll show you its graph. I mean, I hope you're familiar with exponential functions. So like if you take like 2 to the x, uh, you have something that sort of quickly escapes to infinity on the one hand, like as x. So when x is equal to 0, the value of the function is going to be 1, and as x gets large, this quickly escapes to infinity. When x gets very negative, it's going to quickly go to 0. And on the other hand, if you had like y equals 1/2 to the x, the situation is the exact opposite, because if you take a number less than 1 and start raising it to powers, it'll go to 0 really quickly. If you start raising it to negative powers, that's like doing 1 over that. So then it escapes to infinity really quickly. So if you have a positive number for your base, a number that for your base that's bigger than 1, you'll escape to infinity. Your graph will look like this. If you have a number that's between 0 and 1 as your base, then you will look like the green function going down to 0 as x goes to positive infinity. If you just have the number 1 as your base, like y equals 1 to the x, it's just a constant function. And typically, a base for exponential functions is not we only use non-negative numbers as a base for exponential functions. So number e, here's its rational approximation. If you do like y equals e to the x, there it is in black. It's similar to y equals 2 to the x. There are reasons why we like to use e to the x. And yeah, one of the reasons why we like to use it is because of this property. It's true that the derivative of e to the x is equal to e to the x. Answer chat question. So what is e? What does this number mean? Yeah, I guess to recap, it is the unique number such that the derivative of e to the x is equal to e to the x. E is an irrational number. I'll share the Desmos again. E is an irrational number that out to so many decimal places, there it is, roughly 2 And I'll give you a full formal description of what E is later on in the course when we're better equipped to do it. It came from the 1700s from people looking at compound interest formulas. So that's where that comes from. And what is this? So this example, I guess it's referring to something else. Example is kind of nonsense. Skip it. Yeah, this is maybe sort of like a picture of some things I've just shown you on Desmos, which is that if you take different bases for the exponential function, then you'll get different graphs. Like here's b equals 3, 2.5, 2, and then e to the x is somewhere in there. And again, I guess what we're just trying to get across is it's true that if you have b to the x instead of e to the x, then you'll get this formula that the derivative of b to the x is b to the x times natural log of b. Since natural log of e is equal to 1, the derivative of e to the x is equal to b to the x. But what's happening here is the book is basically saying, we're not going to prove this to you right now. We're just telling you the formula. And we can prove it later. So I'd rather have a better discussion of that when I can go to the board and say some things. The textbook doesn't really do a very good job of explaining it, at least in the PowerPoint slides. But yeah, going back to bread and butter questions that you're actually going to be asked on homework and tests, like, oh, okay, find the tangent line of the graph, 3 times e to the x minus x squared at x equals 2. So you're going to want to compute the derivative, of course, at x equals 2. To do that, you should find the derivative, like the general formula for the derivative first. You do that by going using these rules. Constant multiple rule, pull out that number 3. Derivative of e to the x is equal to e to the x, so that derivative is 3e to the x. The constant rule, pull out that -5, and then derivative of x squared is 2 times x. So -5 times 2 is -10. So I want you to be able to rapidly do computations like this, like to get these formulas. Then you'll plug in the number 2 to get, 3e to the 2 minus 10 times 2. And you have to use a calculator for this to get like an approximate value. Can't really do this without a calculator. Take it out to 2 significant figures, find 2.17. And sort of by accident, f prime of 2 and f of 2 happen to be similar values. So you use point slope formula like usual to find the tangent line through the point to f of 2. That's 2.17. But even though f of x and its derivative had roughly the same value at x equals 2, they're very different functions. So here's the graph of f of x, and here's a graph of the tangent line using point slope formula, going through the point to 2.17. So that's how you would do that problem. It's you calculate the derivative, plug in the value to get the slope of the tangent line, then plug into the original function to get the point, then use point slope formula. So hopefully that's that, although I'll do more examples with board work. And just one more theorem for me to pick up next time when we're doing class that we won't talk about today. Although I've got a video on that for showing that every differential function is continuous. Okay, so that's everything for today. Yeah, sorry for the PowerPoint slides. I don't like teaching that way. I think that's like not necessarily the best way to communicate, but I had to do that to preserve the audio for today's class. So thank you, everybody. I'll intend to put up grades for the tests over the weekend, and then we'll give you feedback on that and discuss on Monday. So thank you and have a great day.